Okay, so we're going to continue the lecture from yesterday. But first, y'all got my invitation, right, to see Mr. Bill Kirkwood? Did y'all get that? Nobody's shaking, nobody's nodding. Yeah, you're all invited tomorrow from 4 to 6 if you can come. Bill has a, oops, what? Oh, I got to change that. Oh, actually, it's right here. There it is. So he works at the Monterey Bay Aquarium Research Institute, where they do have summer internships you can apply for. So if you want to kind of find out what they're up to, it's good to check in, and you could chat with him afterwards. He's done hardware. He's a mechanical engineer by training, and he's done a lot of underwater robotics hardware and development. He's also been into engineering management. So he's now a senior research and development engineer. What a great position. It means you just get to have fun all the time. Research and development engineers sort of develop prototypes and stuff. They kind of proof of concept. They don't have to do all the really hard stuff of getting something, a working product. They can just sort of see. They were doing one thing called Shearwater, which was I think it was like a drone that would sort of dip into the water and take samples or something. I forget what that was exactly. It was some kind of a thing they were doing. Yeah, I don't know if that's it or not. Probably not the first thing. Anyway, all kinds of fun stuff. He's been to Antarctica. He's coming back. He just got back from Africa on Tuesday, yesterday. And he's coming in just kind of share about his career. He does this every year. He's got a great career. He stepped from being like in a machine shop to starting his own kind of side operation, making all kinds of money, going various places until he finally got the call to join MBARI as it was just getting started. So they're right here in Moss Landing. If you're not familiar with them, they're associated with the aquarium, but they are a real oceanographic institute. So he will be talking about how he does engineering kind of related to science and stuff. So you're all invited to come if you have any interest in mechanical. He also does sort of he has done some stuff with aerospace. He worked for Lockheed for a bit. Also, you could think of bioengineering. They're definitely doing a lot of sort of well, they're not doing bioengineering per se, but they're doing research about the biology of the oceans, and that requires engineering. Where's the talk? It's going to be in the. You were in that class. You took that class already. You saw him, but you can come see him again if you want. It's in GA 103. Yeah, and also he's got a computer engineering sort of. He got an extra degree in computer engineering or something like that because he needed that for his thing. So anyway, that is good, and a great guy that kind of talks about all the decisions you have to make in your educational pathway, all the decisions he had to make, and how he got to where he is now. So we were working on this stuff yesterday. We were working on equations of equilibrium. We were working on free body diagrams. We got to the point where you should have a pretty good sense of what we're doing on these free body diagrams. And now we're going to solve a couple problems. We kind of got started on this one. This sphere that's sitting on a floor with kind of being cold, and you can kind of guess, as F increases, what's going to eventually happen to the sphere. Gonna what? Come off the ground. Yeah, it'll start to lift up in the air, right? That means the normal force will be getting smaller and smaller and smaller. As F increases, the normal force should kind of be getting smaller and smaller because it's not needing to push back as much. It's fun to just sort of reason through these things, visualize what happens if F increases, and you can sort of see that thing lifting up. That can kind of give you some insight into the answer that you get, whether it's correct or not. So we ended up getting this whole free body diagram thing down, and now we're at the point, and you can see what we did. We started with sort of a description of the problem. We wrote this free body diagram, and then we idealized even more, so it became just this. The actual sphere was just this little dot, at which we can do all of the equations of equilibrium. That is what kind of force system where all the forces are either pointing to or away from a dot. What do you call that? Concurrent force system, yeah. And it is at rest. So because it says it's at rest right here, right? So that means that we call that equilibrium. Meaning all the forces are balancing out, right? And in this case, all the forces are concurrent. That's what we get when we're doing particle. So whenever you have a particle, that means like a singularity where all the forces are going, or it could be a knot in a cable with a bunch of cables attached to it. We're using this particle equilibrium, and particle equilibrium means that the equations are pretty simple. You're just going to get one vector equation because it's in 2D. That's going to become two scalar equations of equilibrium. So the sum of all the forces has to equal 0. And that's the one vector equation. But because it's a 2D problem, you can get two scalar equations out of that. And that will allow you to solve two scalar equations will allow you to solve for how many unknowns? 2. 2 uncs. And what are the two unknowns that we can solve for in this case? Yeah, the normal force N and the tension T. Those are the two unknowns because we know what F is. F is 20 newtons. We know what W is. We just have those two unknowns that we actually have to solve for. And we do that by creating these equations of equilibrium. Sum of the fx's equals 0. So that means we're going to just tally up all the horizontal components of all the forces in that problem, right? And what is a horizontal force in that problem? Sergio, what's a horizontal force? F. Yeah, so F. That's what. What else is a horizontal force? Tension. But it's only the x component of the tension, right? So what would the x component of the tension force be? T cosine 30. And which direction is it pointing? Left. It's pointing in the negative x direction, right? So that's balancing out the F force, right? So we're going to have F minus T cosine of 30. And that has to equal 0. Why? Because it's in equilibrium. Not moving. What about the y forces? Yeah, normal force, starting with a positive one, normal force is pushing up. And what else? There's weight. Is weight positive or negative? Negative, okay, N minus W. And then what else? T sine 30, plus or minus? Plus, yeah. Why is it plus? Pulling the ball up. So it's going to be positive. Yeah. So that equals 0. Two equations, two unknowns, you can now solve it. So it's pretty straightforward. In general, you have to be able to solve systems equations. This one is pretty straightforward because the first equation only has one unknown. You know what F is, so T is just going to equal 20 newtons over cosine of 30. So that equals 23.1 newtons, which you can then plug in to the next equation and solve for N. So this is going to equal N plus 23.1 newtons times sine of 30 minus 98 newtons. That equals 0. And solving for that for N gives you that N equals 86.5. Okay, questions? So that's a pretty straightforward one, but you can get problems that require a little more reasoning in them, right? So this is sort of an interesting problem now where you've got two sacks hanging up here, and sack A weighs 20 pounds, and they're giving us all the angles, but those angles of those sacks and stuff are only going to be true if sack B is a certain weight, and we're asked to find the forces in those cables and the weight of sack B. So, so the thing about this is it's a 2D problem, but it seems like, well, how many cables are there? How many, the forces in the cables, besides the cables holding up the bags, just these horizontal or these other cables, right? There's 3 of them, right? There's CD, CE, and EG. That's 3. And then there's the weight of the bag B, that's 4 unknowns. But this is a 2D problem. I told you you can only solve for 2 unknowns in a 2D problem. How are we going to go about finding these 4 unknowns when we only have 2 dimensions? Kind of interesting situation, right? Is there a way to do it? Well, it's kind of like solving a crossword puzzle. You know, you can kind of work on this part of the problem, and then, you know, you get this word, and then that kind of helps you figure out what that word is, or Sudoku, whatever. For instance, well, there's 2 points of interest on this problem where you could write. Scott, question? Yeah, did you all get that, what Scott says? So he noticed that, so yeah, there's 2 points of interest, E and C there, where you have those are like the 2 particles where you can do particle equilibrium equations, right? This point E has all the forces are acting concurrently, right? Because the cables are pulling along the direction of those cables, and they're all kind of radiating out of that point. And also this point C. And Scott reasoned that, well, at E, you have unknown weight of that bag, but you only have 2 cables attached to that point that have unknown forces. So you could solve for the forces at E with just one equation of equilibrium with those 2 scalar components, right? That'll help you solve for those 2 unknowns. And then you could take that force EC that you find, you know, and turn it around. That's going to be a known force at point C, right? Because whatever force you're pulling at, you know, at E is going to be pulling you the other direction at C, right? And then you only have 2 unknowns there, the weight of the bag and the cable force CD, right? So that's the overall plan. We want to start at the point where we can solve for the forces, and we solve for these 2 forces, and then you repeat that process at point C. So it's a multi-step process. So the free body diagram, let's see here. What am I doing? I don't know if I have that. We can certainly do it. So the free body diagram. Oh, yeah. There we go. Oops. Oh, yeah, right there. Okay, good. So we start with the diagram at point E. And the diagram at point E is going to have a force going downward of the weight of that sack, which is 20 pounds. This is E. We're also going to have TCE pulling us down and to the left at a 45-degree angle. We should label that 45 degrees here. And you also have this TGE pulling us up. And it has a 60-degree angle to the horizontal, 30-degree to the vertical. Okay, so now we basically can write the equations of equilibrium, right? So the equations of equilibrium are going to be sum of the fx equals 0. And you know, I want you to, when you solve these, I want you to write that. I want you to write sum fx equals 0. Why do I want you to do that? Helps me grade your work, right? A lot of people just like write the equations down and I don't know what they're trying to do. And if it's wrong, I can't figure out where you're trying to do fy or trying to do fx. So help me out, write sum of fx equals 0. That's what you're trying to write. And that's going to equal, okay, what are all the x components in this system here? Someone give me an x component. So Ben, give me an x force. Tension CD, did you say? No, we're just constrained here at E. There isn't any TCD on this free body diagram that I just drew. Yeah, so TCE, is that what you're saying? Yeah, so what would the horizontal component of TCE be? Yeah, and is it positive or negative? Yeah, good. So you can write minus TCE cosine of 45, right? And how about another horizontal component, Alec? TGE cosine of 60, and that's positive. Now, one thing that's a typical, you'll see this in the book, they do this also, they'll put a little arrow here when they do sum of fx equals 0, they'll put a little arrow like this, and they'll put a plus by it. I got a little too close to that. What does that mean? That's what you're considering a positive direction in your equation. Sometimes it's convenient to do it in the opposite way. Sometimes if if the problem is sort of a tilted thing where you got some stuff on a plane, you might have, a positive x going, this way. If the whole problem is sort of angled in a way that looks kind of makes more sense to kind of look at it that way. When we work with friction problems, sometimes that's the case. This is a very good habit to get into in your work, to kind of just make it clear, everything out in the open, what you're trying to do there, right? So that's the fx equation. You can do the same thing for fy. You can put a vertical arrow with a plus sign by it. That's going to be what we're calling positive y. And Adrian, you want to give me a vertical force? The vertical force at point E on this diagram, there's only 3 forces. Yeah, so I've labeled the force, the tension, say again, the tension for the, so you see this diagram here at E, and there's this arrow, there's this arrow, and this arrow. They all have vertical components to them, right? So give me one of those forces. Give me the vertical component of one of those forces. Not exactly. Anyone else want to help out? Siri, want to help out? Give me one of those vertical forces. Yeah, equals, let's see, TGE sine of 60, right? Positive, right? Right, because if you resolve this TGE force, which is a 60-degree angle, into its vertical component and horizontal component, the vertical component is going to be TGE times the sine of 60. Right. Okay. Victor, you want to give us another one? Positive or negative? Yeah, negative 20. Okay, that was an easy one. Good call there. And Trent, another one? Everybody agree? Minus TCE sine of 45. That is the vertical component of the TCE force. Okay, you've got two equations and two unknowns. And any suggestions on how you might solve those? You all know how to solve those, okay? Two equations and two unknowns. You could set them equal to each other. Dylan? Recognize the cosine of 45 is the same as the sine of 45 and sub in? Or good, yeah. You see that? Because sine of 45, they actually made this is the same as this, right? So the TCE term is the same on both sides. Therefore, you can move those onto the left side of the equal sign and then equate the TGE cosine of 60 must be the same as TGE sine of 60 minus 20, right? That makes sense? Substitution can work. I find a lot of people kind of make mistakes when they use substitution. So you got to be careful about it. I think the most reliable way of solving it, well, I guess you might have your own way, but I like the sort of the Gauss elimination way, where you can kind of subtract one equation from the other. And I guess you can screw up any ways you try it. You can also use your calculator. You can also use FreeMat. We'll show you how to use FreeMat later on. There's a few different ways of doing it, but you can start by you're taking linear algebra, which is all about systems of equations, and they'll give you a bunch of techniques of solving it. You can also use Cramer's rule, right? I might start with TGE cosine of 60 minus TCE cosine of 45 equals 0, and then you've got sort of TGE sine of 60 minus TCE sine of 45 equals 20, right? That's a typical system of equations. And when you write it where the terms line up, sometimes you can also make some interesting observations. Like if you add those two equations, well, if you subtract the bottom one from the top or the top one from the bottom, you'll actually cancel out the TCE terms as well. And that's pretty much the same thing I think that Dylan was doing. But it's more formulaic. So if I want to take, so if this is 1 and this is 2, maybe I want to compute 2 minus 1, right? If I put a minus sign in front of all the terms on the 1, right? So that becomes a minus, this becomes a plus, this basically, right? That's it. And now I'm going to just add those together. Then you'll see also that these two will cancel out, right? And you're going to just get equals 20, and you're going to get TGE. And you could even factor out the those terms, sine of 60 minus sine of minus 60 minus cosine of 60 equals 20, and then you can solve for TGE directly from that, right? So whatever you need, be comfortable doing this. You're going to do this a lot in this class. You're also going to do 3x3 systems. And sometimes you're going to have 6 equations and 6 unknowns, which you'll kind of knock out equation by equation. So basically solving for those, if you do the math, you're going to find TGE equals 54.6 and TCE equals 38.6. And these are in pounds. And I have some extra space here, but I think I can do it all on one page. So that's all of the first part of the problem. We didn't really finish yet. We got to now find the solve the equations at C to find the extra force in CD and the weight of that bag, right? So we have to write another free body diagram. But we now know that TCE is 38.6, so that removes an unknown from that other point, right? You can't really start at C because you actually have 3 unknowns here at the beginning of the problem. But now that we solved it at point E, you only have 2 unknowns. You can do the rest of them for the second system. So we're going to make another free body diagram at C. And we're going to have a W sub B here, pulling down the bag, or pulling down the knot at C, or that ring. We're going to have TCE here, which is, again, 45 degrees. And it is 38.6 pounds. And you're going to have TCD over here, which is at a 345 orientation, like that. Again, you put everything on that free body diagram that you need to write the equations of equilibrium. Any angles that you know from the problem, any variables that you have to define for the unknown components, any known values. You can just put them all in there so that all you have to do from that point on is just look at your free body diagram. You never have to refer to the actual diagram initially anymore. Okay, so we've got that, and now we're going to start with the sum of the fx's again. So the sum of the fx's equals 0. Again, we can put our little arrow there. Once again, let's see. Emmanuel, you want to give me a horizontal force? Yep, minus TCD times 4/5, right? How about another one? Connie, you want to give us another horizontal force? Yep, positive or negative? Yeah, good. And that's it, right? There's only 2. And now we can do the sum of the fy's. You see how fun this is? It's just such a blast. So vertical force. Joel, you want to give us a vertical force? Okay, WB. Minus WB, good. Corey? TCD times 3/5, positive, okay. Paula? That's it. 3 equations, 2 equations, 2 unknowns. Now we solve those. So cutting to the chase, you'll find that TCD will then equal 34.2 pounds, and W sub B is going to equal 47.8 pounds. And that answers all the pieces that we need for this. Those are the 4 answers. So that's the extent of what we're doing for the most part today and tomorrow. Except we also are going to be doing this in 3 dimensions as well. 3 dimensions gets a little more challenging. But before we do that, let's try a concept quiz. What's the question? Assuming you know the geometry of the ropes, you cannot determine the forces in the cable in which of the system above. And just assume, I guess I'm trying to figure out what these things are. I think this is a pulley. And here you have a pulley like this. Here you have a pulley where the string is like that. And here you have apparently a pulley, or maybe it's a ring. Let's just assume it's a ring. And these are just knots here. Which system can you not determine the forces in the cable? C, right? How come? Because you got too many unknowns. It doesn't mean it's going to fall. It just means you don't really know what the forces are going to be when you got 4 wires hanging up there, right? You can't really figure that out. You can figure it out in this one because you can do the equations of equilibrium here, and you've only got 2 unknowns. You can figure it out in this one. You're going to have to add up to 1,000. But in this one, you've got, if you've got 4 vectors like that, there's no way you're going to be able to solve the equations of the 4 unknown vectors like that. You're not going to be able to solve, right? Too many unknowns. You can only do 2. You can only do 2 at each point in a problem with a particle in equilibrium. So the answer is there are more unknowns than equations for C, right? Because you only have 2 equations and you're going to have 4 unknowns there. So it's really easy to, this is called, that's under-constrained, right? It's an under-constrained system, right? When you have like 4 unknowns but only 2 equations. So the best you can do is come up with like an equation for how those forces are going to be distributed among the 4 unknowns, which will have like 2 variables in them remaining, right? They go over that in linear algebra, right? Have they talked about like the existence and uniqueness of solutions, right? Everyone's like, don't mention linear in this class, please. We don't want to hear it. Okay, there's another problem, but I think this is more of the same. The answers are here. If you pull it up, you can kind of read through them. But another quiz, what is the correct free body diagram of particle A in this system? Connie? D, yeah. It's really quiet. Is it very confusing, or you're all just waiting for someone else to say something? You just like delay the lecture because we don't want to do 3D stuff. You got this one, right? So the second section is section 3.4, and in this section, we bring in the 3rd dimension. So with the third dimension, you've got to deal with just another equation, basically. When you have 3 dimensions, if you have a particle in equilibrium and you have 5 forces acting on it, how many scalar equations of equilibrium can you write for point P? So here's the force, here's the particle, you've got forces acting on it in a lot of different directions. How many equations of equilibrium can you write for that? 3. Yeah, the equations basically are basically on how many dimensions you have in the problem. And since we only have 3 dimensions, you can only write 3 equations. So hopefully 2 of those forces are known. Number 2, in 3D, when a particle is in equilibrium, which of the following equations apply? All of the above, right? These are all different ways of saying the same thing. Yeah. So more generally, you have 3-dimensional systems. You have to be able to figure out the forces and the load. Here's another 3D system, and you've got to yeah, basically have to write equations for those. So the equations in 3D equilibrium are the sum of all the vector forces has to equal 0. And that means, as we already saw, the sum of the fx's in the I direction plus the sum of all the forces in the y direction plus the sum of all the forces in the z direction has to equal 0, or the sum of all the fx's equals 0, sum of all y's equals 0, sum of all the fz's equals 0. So it's either that one, or that one. So we're going to go straight to an example. Permanent tension in the cables AB, AC, and AD caused by the 600-pound crate. So there's sort of some really cool things. It just kind of makes you want to hang up stuff in your home or something, right? Just to kind of see how you can do that. It's cool how you can have these cables that are perfectly horizontal because you got all the vertical lift is coming from this AD cable, right? And these are all taut around a 90-degree angle there at AB. Anyway, very interesting stuff. And we are going to find the forces in those 3 cables, FAB, FAC, and FAB. And we're given the geometry and that the weight is 600 pounds of that crate. No, this is going to be a little more involved because we don't really know the direction. Well, we know the direction of 2 of them, but we don't know the direction of that third force AD. It's sort of it's tied to the geometry. They're all tied to the geometry, but this one's sort of in an odd place, right? We know point C is located at the x is 0, the y is a -2, and the z component is 0. We know point B is located at 2.5, 0, 0. And point D is located at what? -2, 2, and 1. We're going to need that. The free body diagram is going to show you. You need to write these 3D ones here, which is kind of fun. Here's X, here's Y, Z. Oops, I think I messed that up. Yeah, and this is the cable. Change the color here. So you're going to have one force going this way. You're going to have one force going that way. And you're going to have one force going this way. And FAC vector is just going to be the magnitude of FAC times the direction. What's the direction of FAC? What's the direction vector for that? It's minus j hat. Yep, pointing in the minus, pointing along the minus y axis. What's the direction vector for FAB? Yeah, it's I hat. So it's just these unknown magnitude times I hat, and unknown magnitude times minus j for FAC. And then for FAD, well, it's pointing to this point D. Here's FAD. We're going to have to figure out what is the direction of FAD. Yeah, so you can basically start by finding UAD, and that equals RAD, the position vector, remember those, over its own magnitude. So that's going to be D minus A over that magnitude. And that's going to be it's going to be minus 2I plus 2J plus 1K over the square root of the square of all those things. 2 squared plus 2 squared plus 1 squared. So it equals minus 2/3 times I plus 2/3 times J, because that equals 3 on the bottom, and then plus 1/3 times K. So that's our position vector. That's our direction vector, UAD. And our force FAD is just going to equal some unknown magnitude times UAD. Okay, and so we've got to write the equations of equilibrium. We're going to do that on the next slide, if everyone caught up. So the equations of equilibrium is the sum of all these vectors has to equal 0, meaning, now you can do this a few different ways. This is the vector equation, right? You can solve this using a vector equation, and the vector equation, and sometimes that's actually convenient, especially if several of the forces they only have one component in them. So FAB vector plus FAC vector plus FAD vector plus W as a vector is going to have to equal 0. And that means 0 is going to equal, and you can basically write these out as vectors. So FAB vector is just FAB magnitude times I hat, right? And FAC vector is just FAC magnitude times minus J hat, as we saw already. And FAD vector is FAD magnitude times UAD, which is minus 2/3 I plus 2/3 J plus 1/3 K. And then W is just going to be plus 600 times minus K, the direction of that weight. So you have one big vector equation. Right, so we're going to basically group all of the I j and k terms together. So all the I terms are going to be 0 equals FAB. So I got rid of that one. Minus 2/3 FAD. This one right here. For the j terms, we're going to have 0 equals minus FAC. And plus 2/3 FAD. And for the k terms, we're going to have 0 equals 1/3 FAD. That is, let's get that one. And minus 600 pounds. So this last one tells us that FAD has to be 1800. These tend to fall together pretty quickly. 1800 pounds, just solving for that one unknown there. You can then plug this into these two equations. And you'll also find that FAB is going to equal 1,200 pounds, and FAC is going to also equal 1,200 pounds. So what's interesting is that 600-pound crate is creating a lot of force in those cables. 2 or 3 times the amount of the weight of the crate itself. Why is that? Is it reasonable to think that a 600-pound crate is going to require 1,800 pounds of force in a cable to hold it up? Yeah, it will if they're acting at an angle, right? If you want to reduce the force in the cables, what would you do? Yeah, if you just made it vertical, you could just hang it. You could hang that crate from one rope straight up. It would only have 600 pounds on it, right? But you might not have the same, you know, it might not look as cool, for one thing. I think it looks cooler, right, to hang it this way. I would hang it this way if it was in my room, right? It's more interesting. Scott? They're horizontal, or pretty much all horizontal, yeah. So, yeah, so this, you know, this ratio here, actually from here to here is 1/3. That means, you know, you've got to get, this has to be 1,800, because this is the only thing that's providing the vertical force holding up that box is this this vertical part of FAD, right? And so this 1,800 is scaled by 1/3 to get to 600, which is what we need to keep that box aloft, right? So if we lowered point D even further, the force would get even higher, right, in that cable. And if you tried to put point D on the XY plane, the force would go to what? It would go to infinity. You couldn't hold it completely vertical with 3 horizontal forces. You couldn't keep it from falling. It has to sag at some point. Otherwise, the cable would break. Yeah, it's kind of interesting stuff. And concept quiz, when you know the direction of a force but not its magnitude, how many unknowns correspond to that force? One. Anybody else? Yeah, because if you know the direction, you know the ratio of the different components. You just have to know what the magnitude is to find them, right? If you find the magnitude, then you can find all 3 components once you know the direction. Right? So there's only one unknown. And if a particle has 3D force acting on it, it's in static equilibrium, the components of the resultant force of all the forces acting on it, and it's in equilibrium, has to be what? A, B, C, or D? Sorry? B, yes. Individually, these components individually have to sum to 0. It's not that the three added together have to sum to 0. This is actually saying fx plus fy plus fz equals 0. That doesn't make sense. That doesn't make sense either. Yeah, it has to be B. Tomorrow we're going to do this problem where you have only one unknown force, but it has 3 unknown force components, fx, fy, and fz. This one force, F, has to make this whole thing in equilibrium. We're going to figure that out tomorrow. And then we'll do in-class concepts.